Did you know that the way you place a tiny strain gauge on a load cell can make or break its accuracy? A small change in orientation can dramatically increase sensitivity, ensuring precise weight and force measurements in everything from lab balances to massive industrial scales. But how does it work? Stick around and let's unravel the science behind strain gauge orientation and its role in boosting load cell sensitivity. Before we dive into strain gauge orientation, let's understand what load cell sensitivity actually means. Sensitivity in a load cell is defined by how much its output signal changes in response to an applied force. This is typically measured in millivolts per volt, MVV. For a 2 MVV load cell, if you apply 1 volt and full capacity load on the load cell, its output will be 2 MV, and if supply is 12 V, then output will be 24 MV. Higher sensitivity means greater signal resolution and better accuracy in force measurements. Now the big question is, how do we improve this sensitivity? That's where strain gauge placement and orientation come into play. A strain gauge is a tiny but powerful sensor that converts mechanical strain into a measurable electrical signal. It's made up of a fine conductive wire or foil arranged in a precise pattern. When force is applied, the strain gauge deforms slightly, causing a change in electrical resistance. Tensile force stretches and pulls the wire to reduce its diameter and increase the length, causing resistance to increase. Compression causes the reverse of it and reduces the resistance. This change is proportional to the amount of strain, allowing us to measure force or weight with incredible precision. Now here's the game changer. The way a strain gauge is oriented on the load cell directly affects how much strain it experiences, and in turn how sensitive the measurement will be. Let's break it down. Axial orientation. Placing the strain gauge along the primary stress axis captures maximum strain, increasing sensitivity. This is ideal for tensile and compressive force measurements. Shear orientation. In torque and bending applications, strain gauges are placed at a 45-degree angle to maximize shear strain detection. This enhances sensitivity in torsional load cells. But placing a single strain gauge in force is affected by ambient temperature and other conditions like noise. So, to compensate, all 4 strain gauges of the Wheatstone bridge are placed in equal stress to nullify the effect of ambient conditions. It also improves the gauge factor, which is responsible for its sensitivity. Now, what is gauge factor? It is the ratio of change in resistance to the change in strain given. The more it is, the more gauge factor it has, and the more sensitivity it will have. Full bridge configuration. So to get the highest sensitivity, all 4 strain gauges in the Wheatstone bridge circuit are exposed to the same ambient condition while canceling temperature effects and noise and are positioned to maximum tensile and compression strain to amplify sensitivity. In this configuration, 2 strain gauges are deployed in such a way that these 2 always experience tensile force, and the other 2 strain gauges remain in compression force, thus generating maximum deflection in the Wheatstone bridge for a minimum applied force. This arrangement makes the load cell highly sensitive. The key is to align the strain gauges in a way that captures the maximum deformation while minimizing unwanted strain components. Engineers carefully analyze stress distribution using finite element analysis, FEA, to determine the perfect placement. You might wonder, why not just increase sensitivity using electronics? While signal amplification is useful, it also amplifies noise. Mechanical optimization, like precise strain gauge placement, offers a cleaner and inherently stable solution. The best approach is a combination of both: smart sensor placement plus signal conditioning for maximum performance.